moving. I first, oh, this meeting is being recorded. Okay. He keeps moving. I think we first met in Kiev in the western part. Now he moved very, very far to the east, just like me, by the way. And I also moved to the south a little bit, and he remained on the same latitude, more or less. As you can see from the slide, he is now at Far Eastern Federal University in Vladivostok. And he is research active, as you can see, and he is also now in charge of the all mathematics research in that region of Russia. So this is great to have Evgeni Nurminski on board as one of our speakers. And now the ball goes to you, Evgeni. And for Juan, the name should be pronounced like that, Evgeni Nurminski. Very easy, much easier to pronounce than Huabui. Okay, go ahead, Evgeni.
Thank you, Alexander, for such a kind introduction. But we have a lot of I have a lot of slides, so I will not take more time on different distractions. Anyway, good afternoon, Australia, Siberia, good morning, Moscow, Europe. And so we begin I want to talk today on projection problems, which we face in an endless number of applications. Specifically, I was interested first in non-differential optimization, where projection is also quite often used. But then for some practical problem, I became interested in application of this problem, of this idea or technique for linear optimization, especially for decomposing large-scale problems. So this interest in projection was kind of, firstly, it was just practical necessity to do some computations, but then it became interested in also from theoretical point of view, and it is really very rich and interesting area of research, and I am happy to share some of my discoveries in this area with this distinguished audience that I have here. So we start with some standard notations, which are kind of just to introduce some notions where the non-standard part, I think, is this 0, 1 special vector. Oh, just a question. Do you see my cursor?
Yes.
On this? Yeah? So I can use it as a pointer. Good. The inner product, so we are in a finite dimensional space. The elements are n vectors. Inner product is denoted just by, as usual, multiplication. A norm is standard. Chebyshev norm is like given. And I already used to denote standard simplex by this funny notation. Then, oops, sorry. Then we have some notions, of course, also quite standard from convexity, convex hull, conic hull, and also we have finite generation for convex hull and the conical hull. We use certain finite set of points to generate convex and conic envelopes. And also we, for ease of notation, we use the same letter as for linear operator, which is generated by these points. So it's kind of very standard. The only kind of non-standard thing is, I think, this my favorite notation for the support function. But you can just take it as it is. So we will work with two kinds of convex sets. One, actually, of course, they are kind of equivalent. There's the same set of convex bodies. One is polytope. The terminology is rather mixed in this area. Sometimes polytopes are bounded, sometimes they may be unbounded, but we will work only with a convex closed bounded sets. So there is no difference in polytope defined as a convex hull of some finite set of points and convex polyhedron produced by a set of inequalities. They are theoretically, these two definitions are equivalent, but in practice, it may be a big difference whether you are using inner representation or outer representation for the same convex set. There might be exponential complexity for in inner representation of convex polytope, and maybe and the outer representation is a finite. Just a cube is a very simple example. There is another way around also, when a set may have finite or polynomial number of extreme points and have exponential number of inequalities, which define it in an outer representation. So this kind of creates actually a necessity to develop projection operation, for instance, for different representations of convex bodies. And any of them can find its area of where one is more preferable than the other. So first anyway, we consider the most common projection, which is just Euclidean norm distance from given point A to the set X, or in equivalent, we have a least norm problem for the shifted set X. For just a little bit less, a little bit more convenient to use least norm formulation of projection problem. So we stick basically to this, to the last one. So the properties of this projection operation is quite well known, of course. There are some good news and there are not so good news. First of all, of course, it's strongly convex problem with a bounded Lipschitz constant for projection operator. Also, it makes a lot of nice property. However, there are some not so good news that you may have Lipschitz constant equal 1, so there is no contraction for this operator, so iteration algorithms may fail. And even it is not strictly equal to 1, it may be quite close to 1. So the iteration algorithms may be quite slow, as we know from theory and actually from practical experiences. There are, of course, particular cases for some specific algorithm sets, and this boxes, spheres, Hall spaces, linear manifolds. There are just analytical expressions for these projections there. And usually in the articles you read something like that, the people are given an example and say, oh, for a general set that might be not so simple, so we just stick for a moment, we stick to simple sets. The next to kind of trivial case is the ellipsoid projection for ellipsoid. Then it can reduce by duality, of course, to finding the root of the following function, which has rather kind of interesting behavior, but because plane can touch the ellipsoid and the end points. One of them is projection, and there are other roots in this equation which corresponds to kind of a maximum to most remote point and some intermediate points in between. The real projection corresponds to the least positive root of this equation, but it's still a high degree polynomial. And so you might have computational problems with solving this equation. And I know about Lobachevsky algorithm for finding the root of high degree polynomials, but there might probably be, I'm sure that there are many others, but anyway, it is, even simple dichotomy works quite well. For instance, here on this graph, you see the computational time as a function of dimensionality of the ellipsoid. So it can go as even for 1 billion variables, it's just 3 seconds. So it's not a big deal. The interesting case is, of course, canonical simplex, where there are few very interesting algorithms for this. One is Michelot from '86, and maybe less known algorithm by Malazumov and Thomasyan from Leningrad School of kind of Demyanov. And these are, in a way, they are just complementary algorithms. When for both of them, you can construct examples when it takes kind of linear n steps for n-dimensional simplex to project some point. But it is interesting that when Michelor works with such example, it just becomes kind of slow. For 10,000 variables, you have to make 10,000 iterations. But Malazumov-Thomasyan, for the same example, works quite fast. And the other way around, when this one is slow, Michelor works quite fast. There is no theoretical explanation for this, I think, but the behavior is quite interesting. To have a feeling for the Michelor algorithm, you can see the code for this algorithm. You see it's just a few lines in kind of MATLAB, and the performance of the tested performance for this algorithm with randomly generated points to project on standard simplex looks like following. So its number of iterations is basically logarithmic in dimension, which actually demonstrates the typical behavior of this algorithm. Roughly speaking, it halves the dimension of the variables on which it operates on each iteration. So you complete the whole work in logarithmic number of dimensionality. And this solid line shows the average number of iterations for, I don't know, for 100 tests. And these dotted lines and this dashed line, they show the maximal number of iterations for these sets and the minimal number of iterations. They both kind of correspond to the same logarithmic behavior. Then if we look at the general, more or less general polytope projection problem, it is formulated here. We have a polytope given as a convex hole of this finite number of points. And so the first idea was just, okay, it's quadratic programming problem, so why don't you use just the standard tools? But however, if you use it in this formulation, you see that this barycentric coordinates, as they are missing from quadratic part, so your quadratic form is semi-definite, and this is not quite, in my experience, not there are some algorithms, not all algorithms, quadratic programming algorithms are able to work with the semi-definite, but of course it's just less than. You can get rid of the primal variables and stick to the just to barycentric coordinates. Then you have general quadratic form here. And if number of points, vertices here, is greater than dimensionality, that it became degenerate, almost kind of sure. And so solution is not unique. And again, we may face some problems with this with solving it. And also there is certain kind of actually, if you look at this problem, you may guess that not all vertices here are essential for the solution of this problem. The solution, the least distance point may lie on some face of this polytope, which is generated by just a few points from here. But to formulate this problem as quadratic problem, you have to compute all cross products between these vectors, which is probably not necessary to actually to solve this problem. So we again wanted something which will work for our problems kind of in understandable way and with a minimum extra work. So we devised a polytope projection algorithm, which is very simple in idea. There are some data which are extreme points or just a cloud of points which we have to form the convex hull. Then we start with some subset of this point, which I call suitable basis. And suitable basis is that this is such that if you project on the linear space formed by these points, then the projection lies in a convex hull of these points. But the trivial example of that suitable basis is just a single point from here. If you project on a x1, you have x1, which is linear space of x1, or affine space, to be more precise. And also it is a convex hull of this point. So it is not a problem to start algorithm. Then we look for some point which improves this distance, original distance from to the starting base. And if we found such point in the linear space, then we add it to new bases, and we look for points. We project it. This point can be represented as some mixture by its barycentric coordinates, and some of them might be negative. Then it is not a solution to our problem. So we have to do something with this negative, and we have to delete them to throw them out in somehow. And the geometrically, it looks like following, which is kind of simple. For instance, here we have an initial suitable basis, and we project on this L1 linear space, which is formed by these 2 points. And the projection is in a convex hull, so everything is fine. But then we discovered another point, x3 here, which looks like will improve the distance to the convex hull of everything. So we added to these 2 points, it's here. You have now the convex hull like this, and you have another linear subspace which is generated by these 3 points. And we project the origin on this L2 linear space, and we get this point here, and it is outside of convex hull of this new set, I may say. So what we do, we have some previous point here, which is in this convex hull, and one which is outside. So we make a linear homotopy from this point here. We hit the bounds at this point, and it allows us to detect the new basis here. This point can be deleted, and the distance will decrease anyway. When we move from this point to this, you will decrease the distance. And so, and then we have this new point, we have new subset of vertices. I didn't want to make it too complicated, this drawing, so I didn't show the next linear space which will be produced by enveloping this to this new basis. Then we again project origin on this new line here, and so on. That's a kind of iterative procedure, but it is monotone in distance, and it's so bases will not repeat, and algorithm has a finite convergence. So, and its performance was kind of quite satisfying for us. We took some standard QP procedure from Octava, which is kind of MATLAB clone, and compare it with this with our subroutine. And dashed line is QP, and the solid line is our PTP projection. And time is logarithmic here. So for the distance, for the number of vertices, basic vertices of 2000, the difference in time is by the order of magnitude. So it's quite fine. And the time also grows linearly with the dimension, or logarithmic, log linear, what I say, with dimension. So it was quite nice. And if you look at the cost of iteration, that is here just experimental results, and it shows that the growth in for the cost for time runtime for one iteration grows quadratically as the size of the problem. So, which is quite nice. I think it's even better than solution of linear equation. And these tests were performed with dense data, so it's quite reliable, I think. So, but what we still, there is a problem of what we can do with the standard description of polyhedron, which are given as a linear set of linear inequalities, because it is actually quite often used and more need for practice. So, of course, you can theoretically just retranslate it into the extreme point, but that is just theoretically, because almost sure you have exponentially large number of extreme points, and to number them all, it's just out of question. Of course, you can have some hopes for the kind of column generation techniques, which generate extreme points of this polyhedron, kind of responding to some request which is generated by some direction or something like that. But it also requires solving linear programming problem at each step, which is kind of rather complicated. I say even now there are very efficient algorithms for doing that, but I wanted to solve a projection problem without any auxiliary linear programming problems because of high dimensions or something like that. So what we then, what kind of tricks we can use to convert polyhedron problem into polytope problem without having exponentially large number of points and things like that. So, but there are kind of interesting trick here. First, we convert this inequality in almost uniform set of inequalities with just one non-zero right-hand side equation. It's also kind of very standard. And this part describes us some cone, and this is the hyperplane. So you have a well-defined cone and a single hyperplane which crosses this cone. So we denote cone as K and the hyperplane as H, and this must be A here. This special vector, which has just one as the last variable, which corresponds to this Xi. So then what we do, we just exercise in convex in duality so we split the variables into one is from K cone and one is from hyperplane, and we ask for them to be equal, and we leave a quadratic term associated with the conical part of this constraint. And then we dualize with respect to this equation. It's kind of similar to monotropic programming, actually. And then we delay taking max with respect to these dual variables to the last stage. And as an inner problem, the objective here becomes separable in x1 and x2 variables, and we have internal mean with respect to x, which consists of sum of two terms. One is simple quadratic optimization without no constraint, with no constraints. So it has a kind of analytic solution. And the another part, which is indicator function of so far as variable x takes its values from the unbounded cone K, this mean is just 0 infinity, depending on u. Is u in a dual cone or not? So it means that finally we arrive at the following expression, reformulation, where you just have to project this point on a dual cone for the and the dimensionality of this problem is just the same basically as the original problem. So which is nice because no exponential, no any exponents here. And also this part is very simple actually. It is a quadratic in this variable. And it is 0 at when theta is equal to 0. So it can be expressed as a value of this projection for theta equal 1 times square times theta square. So you have again actually a quadratic problem here in one variable. So you go to school and ask pupil to solve it, and then so the actual problem is to find the coefficient of this quadratic form. And it is equal to projection with theta equal 1. So you have to take just the point E, project it on a dual cone, and that's it. And so here we have also specific problem projecting on cone. We first make some kind of algorithm very close to spirit in the original PTP problem. But and it works quite nice. You see that is a I believe it is time. No, that's a relative error in projection with iteration. Somehow, I don't know why, but this x is somehow dropped from the figure, and so far as is it logarithmic, you see the linear convergence, and then it became more like a quadratic convergence, and it's dropping to basically to machine accuracy, because for that size of problem, you kind of you must be very lucky to reach 10 to the 10 or something like that, to the minus 10 or something like that. And the indicators of convergence for these algorithms are quite insensitive to the size of the problem, which is nice. For instance, here we have two computer runs. One is for 1,500 constraints. Second was 2,000 constraints or vertices or generators in the cone. And the rates of convergence are kind of rather close. So, and all in all, it took about 500 iterations to reach the, to solve the projection. Here are just numerical results, summary of different tests we made with 1,000 variables and the number of constraints like this. What is nice is that in none of these cases we observe no fails, so that's quite reliable. But then I thought about the different idea, which is based on a simple observation that we may truncate the cone to the polyhedron directly by taking the set of generators for this cone, adding origin, and considering the convex hull of this construction. So, of course, when generators looks like this, our projection on this polytope is not a projection on cone. But we can scale these generators without changes in the cone. So if we move it some way up or further from the origin, you will see the picture like this, and the projection. And for this case, projection on the polytope will coincide with the projection on the cone. So the question is actually how far we can move. We should move these generators. How much we must scale them up to reach this situation. Of course, we can use kind of a recursive doubling, something like we try 1, if it doesn't work, we try 2, if it doesn't work, we try 4, and things like that. And general estimates for the worst case estimates for such scale is rather nasty. It's like exponential in dimension for the finite arithmetic or something like that. It's similar to no, it's the same estimates for, as typical for interior point algorithms and ellipsoid algorithm and so on. But there's another very simple way to obtain this scaling factor right away, just in two, or actually just in one projection. And this is the following. It's here. You have to look at the distance from the origin to your generators and compare it with the difference to your projected point. And if by dividing this by this, we obtain the low kind of a suitable bound for this scaling factor. It's enough to select this scaling factor of that value, of the order of this value, and then problems become equivalent. The theorem which established this is the following, that if inner product of this vector to this vector is less than the square of this B mean, then it's fine. Then your scaled, truncated scaled cone will give you projection. And it is quite easy to see that this you can always find a scaling factor which will satisfy this inequality, because the distance from origin to the set of generator grows roughly linear, or exactly linear with the scaling factor. So this part is quadratic in the scaling factor. So, and it grows faster. So it's a kind of and this is not quite, and it is not very kind of, it gives you not extraordinary large scaling factor, so it makes sense from the point of view of numerical stability of the algorithm. So that's actually the final setup. You have two phases. One is in one phase you compute this scaling factor by projecting a zero on a set of generators, and then you scale your set of generator with this constant, and you project it second time and obtain the projection on the whole cone. So, and here are some numerical experiments which were also rather interesting. In each, there were 3 sets of data, and these sets were different in the total number of data. So the product of number of variables times the dimensionality is constant for each of these sets. It's kind of megabytes that you need to represent your problem in a computer. So for A, it was million double digits numbers, B 2 billions, and C 3 billions. And then we use different proportion. You share this billion between number of variables and number of and the dimensionality. And you move from problem with just a few constraints, but high dimensionality, but just a few constraints. And up to the opposite case, when you have kind of low dimensionality, but huge number of points, like a kind of machine learning examples. And interesting that, and we look at the computations for both for phase one, this is a kind of scale to find the scale, and for phase two, for a final projection. And it's interesting that the most difficult problems, which they are concentrated at the lower end of this. It's not surprising actually, because when you have many points, it's small, it creates small facets on a convex hull, and so you have to move from one to one, spending some time in recalculation on different recalculation. But anyway, the performance was quite nice. So actually, that was just an attempt to find some new ideas for solving linear programming problems. And that was actually the starting point for the whole enterprise, one may say. We looked at the standard linear optimization, and noted, probably it's kind of everybody knows, but so far there were no proofs that you can solve a linear optimization problem by projecting some faraway point back to the feasible set. And this point is obtained by moving in a direction of minus objective. So that involved some kind of interesting convex arithmetics and so on. And so far, the result is the following. It's okay if you have the unique solutions for both for primal and dual problems, formulation of this linear optimization problem. Then, of course, the dual cone at the optimal point is solid. So, and the vector of objective function is inside of this cone, and which doesn't matter which starting point here you have. By moving from this starting point in a direction of minus c, sooner or later you will arrive to dual cone, because it fills the whole space actually, and by projecting this back to feasible set, we have a solution. Oh, and that's how it works compared, for instance, to standard simplex. This is just kind of toy linear programming problem. And if you start from zero with simplex or with objective vector like this, you will move to this vertex, and there is no other way to arrive to optimal point here, only by going through all vertices in this polyhedron. It's kind of this kind of twisted cube minty example, I think. What the projection subroutine in this way works like following, that we took this direction and go somewhere far away, which is symbolically represented by these dots. Actually, it was not so far away. It was sufficient to multiply it by 3, or by 3. And then we projected it in 2 steps to this optimal point. So it was quite fine. The idea was not to beat some interior point algorithms or something like that, which are quite very, very efficient, but to look for some additional possibilities in decomposition of linear programming problems. Because we faced, it was purely practical necessity. We were asked by some railroad Russian company to solve the problem of reallocation of empty carriages all over Russia. And you can imagine from Vladivostok to Kaliningrad, it's 10,000 kilometers, more than 1,000 railway station, and the number of cars is something like 200,000. So it was, and it should be planned for kind of for months. So there is a dynamic involved in all this. So it was kind of very huge problem. And so it was a kind of interest, and without any kind of convenient structure, because there were constraints of different kinds in this problem, not only kind of routing or something like Kirchhoff laws and so on, law of car conservation, but also some number of technological constraints and so on. So, so we try to look at something, what we can do with this problem. And the idea of the composition consists in the following. So, okay, we can represent our feasible set as a convex hull of this point. That might be polytope points given us from the very beginning, just like machine learning. But it may be the generators coming from this conical reformulation of linear programming problem. But we can split actually this set in subsets of different sizes. They may even overlap and something like that. It doesn't matter. The convex hull of these subsets, each of them is a convex hull by itself. It's still the same set, X. So we can hope to solve a projection problem, in fact, by projecting on a separate subsets in this representation. And the projection is maybe very simple, in fact. It depends how clever you are in choosing these subsets. For instance, in the large-scale problems, they are all sparse, as we know. Okay. So these vectors are rows of this huge sparse matrix. And as they are also sparse, because problem is practically square, we have a good chances that these vectors are orthogonal. And hello.
Everything is okay. Go on.
Okay. Am I? Okay. I almost finished. So so if you try to project on a set with the orthogonal vectors, you have this matrix in projection operator is diagonal. So your projection operation is linear in complexity. So it's a kind of a very useful thing to use. So, so the algorithm which we first tried was the following. So we have some idea of the solution of this projection problem, which is that zero. Okay, it can be chosen anyway, yeah. Then we add this point to each of these members of this cover and solve the least distance problem for each of these subsets, enhanced with this new point. And we have number of this solution. Okay, and then we replace this initial Z with this new point, distribute it again to all members of this, to all members of this covering, and again solve projection problem, get a new candidate for the solution, and so you in fact, you kind of loop between two steps, decomposition and coordination. And it was a catastrophe because it was extremely slow in convergence. So that was first very disappointing. But then we saw that, okay, but nobody wants us to keep the same cover for the whole run. It can be changed dynamically, so you can collect some promising generators or points in one good set and delegate all the others, which are probably not necessary, are not interesting from the projection point of view, in some kind of waste bin. and then, and that was a revolution, I may say. It starts working quite fast. But unfortunately, at that time, railroad company, there was change in administration there. Some other oligarch bought this company, and he had some another ideas what to do with this whole and this company. So we didn't continue. But the other application which created the interest in the projection problem is, of course, non-smooth optimization, and one is based on the idea of conjugate gradient algorithms. So we look at gradients or subgradients collected during the optimization process and try to find a descent direction as the kind of common vector in this collection. And that was suggested by Wolf already in '75, but there are some other extensions up to now. The interesting that it can be used also for variational inequalities, the same idea. But the other idea was what I call the conjugate epi-projection algorithm. And to just, in a few words, it's the following. So we can, if we look at objective function of optimization problem, it is can be considered as a computation of conjugate function at zero value. So you kind of invert. You have zero gradient, and you want to know the derivative of this function at zero, which is the solution. Okay, and maybe I'll just show the picture of this idea. So you have a space of conjugate variables, you have epigraph of a conjugate function, and you have a value of conjugate function at zero. And what you do, you move from on this vertical axis in extended dual space in the direction of this point. Well, how you do it? You do it the kind of a Newton way step. You project point on the epigraph, then you have a support plane here, and you use it to cut to obtain the next iteration, the next approximation for this. And from here, you again project on the epigraph, and you get support plane, and you of course, projection on epigraph is not kind of implementable immediately, because it's an implicitly given set and so on. But there is one operation which is easily executed for such set. That is, if you take any vector to find the support plane for this epigraph is easy. It's just enough to compute the primal function at this point. So, but anyway, for this conceptual idea, we have the following convergence results. So if F is just convex, no Lipschitz, no something, and no nothing, then you have superlinear convergence, which is out of nothing. And then if it's something which I call subquadratic, which means that it lies above some quadratic support, and it may be piecewise linear, so no second derivatives, but if its general behavior kind of is above the quadratic, then you have a quadratic convergence like Newton. And then if F is has sharp minimum, then that means that 0 is in the interior of subdifferential set at the optimal, then convergence is just a finite. It should not be piecewise linear or piecewise quadratic or nothing. It's enough to have sharp minimum at the optimal point. So it's quite encouraging, and so we will try to make an implementable version of this algorithm with, of course, with kind of approximate projection here. And approximate projection can be obtained by approximating polyhedral approximation for the epigraph and things like that. And there's a number of other ideas how you can improve convergence. One we tried with Evgenia Vorontsova. I wonder if she's here, but anyway, we tried to add some extra cuts to this epigraph, because of course this epigraph is kind of huge, and it contains parts which are absolutely out of interest. So why don't we cut it from above somehow? And there are many ways which we can do that. And this additional cuts produces auxiliary problems which are of kind of steepest descent or linear sub-optimization and things like that. If you add one cut, you have auxiliary problem of linear sub-optimization. You do some line search. If you add two cuts, you have auxiliary problem of convex optimization in 2 dimensions. 2 dimensions is maybe, then I heard very little about the low dimensional convex optimization. Just, of course, there is this center of gravity algorithms by Levin and forgot the name of this American mathematician who suggested it in 50s or something like that. And it's theoretically optimal, but practically implementable in just low dimensions. But 2 is already something, but it will be interesting to try that. So if we can kind of cooperate on that, if somebody is interested in. So I think I'll finish here because I already overtimed my time. So, and I may take any questions if you hear me and if I hear you. Hello.
Okay. We can hear you very well. Thank you, Evgeny, for your presentation. Indeed, an interesting presentation, and indeed we are over the time limit, but you did your job well. We don't seem to have plenty of questions in the chat area, but it is still not impossible for someone to ask a question. I just want to mention that for everybody that the presentation is, why are you showing me on your screen, Evgeny?
I don't know.
Anyway, thank you for promoting me and demonstrating my haircut.
Okay,
everybody has probably noticed that it all comes from practical applications, and Evgeny noticed some transportation problems. There's 10,000 kilometers between Vladivostok and Kaliningrad, and thousands of railway stations, hundreds of thousands of cars, etc. I just have a feeling that in that huge country, there are plenty of applied problems which could lead for applications for probably all participants of our seminar. And if someone has ideas, please contact Evgeni Nurminski. He is in charge of that region. Any last minute question, if we have? We have plenty of thank yous in the chat. So I've already thanked the speaker on behalf of our participants. I don't see any questions in the chat. Any last minute question by using audio? So if no questions, thanks again, Evgeny, for your nice presentation. You reminded us about projections and stuff like that. We hope to see you again in Australia.
Sure, I will.
I see a few Russian names in the audience, so please also volunteer to present at our